Welcome to this explainer. Today, we're going on a bit of a journey, tracing the actual life cycle of data. We all deal with sprawling, messy data sets, right? But we're going to look closely at the mathematical mechanics of how we take those chaotic, raw numbers and literally transform them into clear, visual stories that our brains can instantly process. Let's dive right in.
But before we even get into the math, we've got to look at where this all started, because the history here is actually pretty fascinating. The word statistics first popped up around the middle of the 18th century, and whether you trace it to the Latin word status, the Italian statista, or the German Statistik, they all translate to the exact same concept, a political state. You see, originally, statistics was strictly a tool for governments. It was all about statecraft, collecting data for administrative purposes. Fast forward to today, though, and the scope is vastly wider. It's now a foundational branch of mathematics that we use in almost every field of inquiry imaginable. So here's our roadmap for today. We're going to cover the meaning of statistics, define our variables, explore the power of frequency, masterclass intervals, and finally graph the data. Starting with Section 1, the meaning of statistics from chaos to order. We're essentially taking deliberately collected numerical facts and meticulously organizing them to shed some light on a specific inquiry.
And that brings us to the actual materials we use in Section 2, variables and raw data, the building blocks. So when we're dealing with the variables, those shifting quantities we actually want to measure, they split into two distinct types. On one hand, we have continuous variables. These can take any numerical value within a certain range. Think of rainfall records or someone's exact height, which you can measure right down to the millimeter. But on the other hand, we have discrete or discontinuous variables. These simply cannot take fractional values. The classic example, the number of children in a family. You can have 1, 2, or 3 kids, but you mathematically cannot have 2.5 children. It's just not going to happen.
Now, before any data is processed, it's just raw data. Think of it like a really messy room. It's totally unstructured. The very first step in gaining some control is creating what we call arrayed data. And that simply means arranging the numbers in ascending or descending order so we can start spotting initial patterns. Suddenly, all that chaos actually starts to make a little bit of sense.
Moving right along to Section 3, the power of frequency, counting the chaos.
Let's look at this jumble of numbers. We've got the raw shoe sizes of 19 different pupils here. Just staring at this disorganized block of data makes it really difficult to pull out any immediate meaningful insight, doesn't it? It's just overwhelmingly hard to interpret anything from a mess like this.
But by implementing a simple tally system, we can instantly consolidate all that. Grouping the occurrences transforms that chaotic raw array into a clean, highly organized, and easily readable frequency table. Notice how crossing that fifth stroke over a bundle of 4 just makes it so much easier for our brains to process?
And that brings us to an absolutely foundational concept: frequency. It's honestly exactly what it sounds like. It's simply the number that tells you how many times a particular piece of data appears in a given set. So, in our shoe size example, the size 6 appeared 8 times. That means the frequency of size 6 is 8. Simple as that. And a table showing these numbers, we just call that a frequency distribution table. Next up, Section 4, mastering class intervals, grouping the data. When data sets get really massive, like, say, a class of 32 students taking an exam with marks ranging from 1 to 50, we have to group our frequencies into class intervals. Now, there are 2 main ways to do this, and it is absolutely vital to know the difference. First, we have an inclusive distribution. Notice how the upper limit of that first class is 10, but the lower limit of the next class jumps to 11? They don't actually touch? Contrast that with an exclusive distribution. Here, the upper limit of the first class is 20, and the lower limit of the very next class is exactly 20. They coincide perfectly. So why does this matter? Why do we care about this distinction? Well, think about it. If a student gets a score of 10.5, where does it go in that inclusive model? It literally doesn't fit anywhere. There's a gap. To ensure true continuity and to get the correct class limits for our final visual graphs, we absolutely must adopt an exclusive distribution. Fortunately, converting those inclusive intervals over to exclusive ones is a super straightforward formula. Step 1, you just find the difference between the upper limit of one class and the lower limit of the next. Step 2, divide that difference by 2. That gives you what we call your adjustment factor. And finally, step 3, just subtract that adjustment factor from all the lower limits and add it to all the upper limits. Here is exactly what that looks like in practice.
Let's say our adjustment factor is 0.5. By subtracting it from the left side and adding it to the right, our old broken intervals of 1 to 10 and 11 to 20 magically transform into 0.5 to 10.5 and 10.5 to 20.5. See how the limits now touch perfectly? We've successfully created true unbroken class boundaries. Okay, before we finally graph this out, there is one last term to tuck into your tool belt, and that's the class mark. This is simply the value perfectly midway between the actual lower limit and the upper limit. You just add the two boundaries together and divide by 2. Keep this mid value in the back of your mind because it's going to be our secret weapon for the final step. And we've made it to section 5, graphing the data, the visual payoff. We've arrayed, tabulated, and grouped our data into continuous boundaries. But ask yourself, when you're reading a scientific article or a news report, how often do you just skip right over raw columns of figures? Usually, you only get a kind of feeble idea of what they mean, right? So how do we make this data leave a more lasting, visceral effect on the mind? This brilliantly illustrates the solution, the histogram. In this graphical representation, we mark our continuous, unbroken class intervals right along the horizontal x-axis, and we plot our frequencies along the vertical y-axis. Then, rectangles are drawn with their bases on those class intervals, and their heights are proportional to the frequencies. It's incredibly eye-catching and instantly readable. Now, I really have to point out a vital technical distinction here. A lot of people confuse a histogram with a standard bar chart, but they are absolutely not the same thing. In a regular bar chart, only the height of the bar matters. But in a histogram, because the bases represent actual mathematical intervals on the x-axis, the height as well as the width of each rectangle matters deeply. It's a really important distinction. And this builds directly into our next, even more sophisticated tool, the frequency polygon. If you take that histogram we just made and you locate the exact midpoint at the very top of each horizontal rectangle, you can draw straight line segments connecting them all together. The geometric figure you get by joining those midpoints, that is your frequency polygon. Now here's where that secret weapon I mentioned comes into play. By comparing these two approaches side by side, we see the true value of the class mark. Because we already know the mid-value of our intervals, we can actually plot those points directly on the x-axis. This allows us to map out a perfectly accurate frequency polygon entirely on its own, without ever needing to sketch out the underlying histogram bars first. It's a real time saver and incredibly efficient. Which brings us perfectly back to where we started. Statistics really is the art and science of collecting, organizing, and presenting data so that true, actionable conclusions can be drawn. We took a messy room of raw numbers, arranged them, built continuous boundaries, and eventually constructed visual monuments of truth. So I'll leave you with this. The next time you're handed a pristine, simple chart in the news or at work, will you be able to look past it and spot the chaotic, raw reality it was built from? Thanks for joining me on this explainer. I hope you see numbers just a little bit differently now.